Okay, all right. So we still have 2 outstanding homework assignments. Okay. Are there any questions about the homework assignments? Are there any questions about how to get started with the homework assignments, or anything about the concepts involved? Yes, go ahead. Uh-huh. We want to swap whatever content is at the address. Yes. Uh-huh. Sure. So that's a good question, because the swap subroutine is supposed to swap whatever the parameters point to, and not the parameters. And so to clarify that point, okay, I know this thing is working. It's just the distance of the mic. So is that volume okay, or too soft, too loud? A little soft? Okay, I can crank it up a little. How about that? Okay, great. All right, so just a quick reminder, this is a computer lab, so no drinks on the desk, please. Because a professor actually did that and drowned one of the keyboards. And then the lab people, the people who maintain the labs, they got a little bit unhappy about it because the keyboard was swimming in coffee. No, it wasn't that one. It was at the instructor workstation, and that's why they were able to say, so which professor did it? They knew it wasn't a student. All right. So I'm going to talk about what you just mentioned. So let's go ahead and take a look at, because I think this is going to be a useful discussion, not only for assembly programming, but also just in general, your understanding of C. So we'll implement a swap subroutine, and we'll kind of do it the same way that we did before. So we have pointer A, and then we have pointer B. Okay. And then in the subroutine, we have a local variable, uin8 underscore t, and I named it t in the homework assignment. So in the original code, this is what it looks like. T gets whatever pointer A points to, and then pointer A gets whatever pointer B points to, and then pointer B, or whatever pointer B points to, gets whatever T it has. So this is the sequence of a swap subroutine. We basically use T to store whatever pointer A is pointing to, because it's going to be destroyed in the next statement. So we need a place to put it first, and then the last statement on line 6, we're retrieving the original value that was pointed to by pointer A, so that we can update pointer B, so that the position or the location pointed to by pointer B now has the value of whatever the value was that was pointed to by pointer A. So we're going to look at several variations of this code, and then we ask, well, maybe just one variation. So let's say someone forgot about the pointer thing here. So the code became this. Okay? So when the code became this in C and C++, the compiler will complain about it. The reason why the compiler is going to complain about it is because the type of the right-hand side and the left-hand side do not match anymore. So when you look at T, T is a uint8 underscore T is an unsigned 8-bit integer. But when you look at pointer A, it is a pointer. It is the address of an unsigned 8-bit integer. So the types are not compatible. So the first line 12 is going to have a compiler error. It's not a syntax error. It is a type mismatch error. Same thing is going to happen with line 14. Line 13 is going to be okay. Okay, there's no syntax nor type matching error, but it's actually not performing the right operation either. So when someone look at the output message or the error message of this code, one way to fix it, which is not going to fix the problem, is going to be something like this. We'll just change T so that T is now a pointer to an unsigned 8-bit integer. So now there's no type mismatch problem anymore. There's no syntax error. But when you run this code, it's not going to do what it is supposed to. Because what it's going to do is it's going to exchange the parameters themselves. but not what the parameters point to. Okay, so that's I hope that answers your question. Yeah, because the differentiation between the original version of the swap subroutine and the second subroutine is just that. Are we swapping the parameters, or are we swapping what the parameters point to? So is that answering the question? Okay. Yep.
I'm just wondering if like the second portion of the code will even work. Is like if we just want to swap the addresses, and if the content get destroyed by any chance, so like we will have like garbage in those addresses.
Say that one more time with the second one, right?
Yeah, like the one that you pointed was like because it had bugs, right? Because we're not changing the content, we're just changing like the addresses, correct?
We are only changing the parameters and the local variable, which are
correct.
Pointers. Correct.
Which are pointers. And
yeah.
We're not like dealing with the content themselves directly.
Correct.
So if we change just like the addresses, I mean like if we just assign like it's like T is a pointer, and it's like a pointer which has an address of the unsigned int, which is 8-bit. So, and we're not dealing with the content. Is it even gonna work?
Is it gonna work? The second piece of code is going to work, but what it ends up doing is exchanging pointer A and pointer B as parameters. So if you put a breakpoint right here at the end of the subroutine on line 15, and then you examine the values of pointer A and pointer B, you will find that pointer A and pointer B are exchanged. So it will get that done, but that's not what we want the subroutine to do. We want pointer A and pointer B to stay put, but we want the content pointed to by the pointers to exchange. So it will accomplish something, just not what we want. Because to the caller, it has no side effect. The caller calling the second version of swap is not actually getting anything done. I mean, it executes, it's not going to crash, but it's not doing anything that is useful either. Is that okay? Okay, so in C and C++, there's one way to, yeah, go ahead. Oh, okay, I thought you had a question. So in C and C++, there's a way to correct this particular problem, like making sure that this does not happen. We can use the concept of a const. So now the question is, where do we put the const? When we have something that looks like this, pointer A is a pointer to an unsigned AB integer. There are two places we can specify the word const. Okay? In some cases, you can use both. In other cases, you should only use one. In some cases, you should use none. So now the question is, where are the potential spots to put that const, the two potential spots to put the const keyword, and which one should we use in order to make sure that the second version of swap won't even compile? One place is right here, where the blinky cursor is. That's the first place we can put a const. And what that const is going to say is, whatever pointer A points to cannot change. Okay, that's what the const is going to do when it is before the type that is being pointed to. The second place to put the const is right here. Okay, so when you put a const here, then it becomes the const applies to the pointer itself. So that means you can change whatever it's pointing to, but you cannot change the pointer itself. So in this case, it is this position that we want where the const is supposed to go, and not in the first place. Because if we put a const here in the first version of the swap subroutine, it's not going to compile. Even though it got the correct logic, it's not going to compile. But if we put a const here, then both versions will the first version will compile and run correctly, but the second version won't compile because we attempt to change the pointer themselves. Okay? So once again, this is not an assembly programming concept thing. It is actually C and C++. But it does illustrate something that is really valuable when you're using C and C++ as opposed to assembly language programming, is the more you specify rules where the compiler understands and try to enforce, then you have a better chance that the compiler can catch programming mistakes. But in assembly programming, there's no such thing, okay? Because here are the registers, A, B, C, and D. Okay, what do you want to do with those registers? Anything you want to. Do you want to treat register A as an address? Sure, use LD or ST instruction. It will be treated like an address, right? Do you want to use it just like an integer? Sure, go ahead and compare or add or subtract. And the assembler doesn't care. And here's register D. It's really special. It's the stack pointer. And then somewhere in the code, I decide I'm going to use it as a temporary register. The assembler says, sure, go ahead. It is one of the general purpose registers. You can do whatever you want. So that's why C and C++ programming is better in terms of efficiency, in terms of how much time you have to spend to write the code and then to debug the code. The amount of time you spend to write the code is actually not that much compared to how much time you have to spend to debug code. And that applies universally, okay? It's not just in assembly language programming. But in assembly language programming, that proportion is surprisingly high on the side of debugging. So for every 10 lines you write, you might spend a lot more time to debug those 10 lines compared to like C and C++ programming. So I'm hoping this kind of answered the question in a thorough way. Okay. Any other questions? Any other questions regarding maybe the recursive subroutine stuff? Fibonacci. Was it? Yeah, I think it's Fibonacci, right? So are there any questions about the Fibonacci homework assignment? That one is due tomorrow, and then the swap subroutine is due today, at the end of the day. So I cannot show you the solution because no questions? All right. If there are no questions, we'll continue to talk about structures because I think we got started with structures before. So we'll go ahead and start with, we'll go ahead and write some code using maybe even arrays and structures. So let me go to the class note here. So we are pretty much close to the end here. These links you cannot see, because, they're actually a part of the homework assignments for one of the semesters. So what we'll do is we're going to take a look at C code first. And then we'll start to think about the assembly language implementation. So is that okay? Can I erase this? Okay. Pretty sure the recorder is still on. Let me just double check. So the recorder is on and the voice should be good too. So that should be fine. So I'm going to remove this. So we'll start with a struct definition and we'll call this a node. So the node here, the word node with an uppercase N, is kind of the same as a name of a class, okay? Because in regular C programming, they don't have any class, and that's why C++ exists, okay? Because regular C is not object-oriented, so it has no concept of a class. But a struct is basically the basis of what became a class in object-oriented programming. So in this class, as an instructional class, we only talk about structures and not classes. So we are not getting into object-oriented programming. So when we define the structure here, and the difference is in terms of syntax, struct in C requires a semicolon after the struct definition, but when you're using C++, there's no need to use a semicolon after a class definition. So there are minor differences here and there. So what we'll do is we're going to say uint a_t. This is our value. So each node has a value associated with it. And then it has a next pointer. So the next pointer is struct node star p pointer to next. Okay. So we'll take a look at this definition here. How many people feel comfortable with this definition? It's like, yeah, I know what it means. Okay. Some people are. And some people are not comfortable with this. Okay? That's fine. Okay, so let me give you another example and see if you have any question about that one. So if I say, alternative node, okay? And in alternative node as a structure, it has a node pointer, okay? And then we change this one to alternative node. Okay, just in terms of syntax. Okay, don't ask about how this is all going to be used, but it's just in terms of syntax and the meaning. Are there any questions about this, or do we feel comfortable about this one? Because each structure only has a member that refers to a structure that is not where the member belongs. Is that okay? All right, cool. So now I understand where the confusion or where the question really is. So the question really is not about pointers. It is about how can we have a pointer to the very same structure that the member belongs to and have that as the type of a member. Well, it's kind of the same thing as saying a house is a class, okay? So you can basically look at the description of a house as a class. And then inside the house, we might need to maintain addresses of other houses. Is that a problem? Well, then why is this a problem? Because a node is a structure, it has several members, and one of the members, in this case p next, turns out to have a type that is a pointer, and it has to point to another node. Okay, so is the confusion because of, well, since we have not really finished the definition of struct node, how can we use struct node as the type of a member? Is that where the confusion is? Or not? Okay. So in that case, let me show you the main difference between why that would not be a problem. If this thing is gone, then we have a problem. This is definitely a problem because the member of this structure is the structure itself. So it becomes infinitely recursive, and there's no way we can actually resolve what the structure should look like. Okay? But once we add a pointer here, it is no longer an issue. How big is a pointer in the toy processor? What I'm really asking is when you use LD and ST, okay, how wide is the address that you can specify in those instructions? Not 2 bytes. It's only 1 byte because ST and LD can only use a single register to specify the address, right? And how wide is a single register in the TTP? Only 8 bits. Okay, it's only 1 byte wide. Okay, so that applies to, this is a pointer to another 8-bit integer. Okay, it's only 8-bit wide or 1 byte wide. But it also applies when it is referring to structures. So that means p next is only 1 byte wide, regardless of how much stuff is in a particular node. Is that okay? So so there's no problem now. Okay. In other words, it is almost the same in terms of how we allocate and how the structure itself is actually structured. If I change this to this, it's the same. Type checking wise, it's not. Okay, type checking wise, this is saying p next can point to just about anything. Okay, because you have to cast it back to a void pointer before the assignment can happen. Okay, so it's only for type checking purposes that we refer to this as a pointer to another struct node. Is that okay? So it makes a big difference whether the member is a pointer or not to itself, to the structure that you're defining at that point. Is that good so far? Question? Yep.
Is it similar to linked list?
Yes, I can use this to create a linked list, which is kind of the purpose of this whole thing. All right. So are we good so far? Good? Okay. So now we say in main, okay, we're going to make an array first. So in main, I'm going to create an array of structures. So it is struct node, and we'll say nodes, okay, in plural, and we'll give it a certain number, okay. We'll use a const int here to define the number of nodes here. So we'll just call this number of nodes, and we'll initialize that to 5, okay. So in this case, I can use the const and say, I'm defining an array of 5 nodes exactly, like so. And I want these 5 nodes to point to each other. One would point to the next one, and then the next of the next one points to the next one until we get to the end. Then the p next pointer would be a null pointer to indicate, okay, we're done. This is the last one. It has no next, compared to the other ones. Okay. So let me see, how many people are getting the idea or the concept? Okay. And how many people want me kind of to use a picture to illustrate it? Always helps, right? Okay, so we'll do that. Let's see, is Zerno still up? I have one Zerno earlier, but that was somewhere else. So I'm gonna start one up here. And by the way, Zerno is a program that also exists for Windows. It's a great tool. If you want to fill in like a PDF form, but the PDF itself is not really a form, it doesn't let you edit and change stuff, Zerno can do that. So it's a great tool. And then you can save the PDF, you can save the documented version as a PDF again, and then email it back to whoever sent you the form to begin with. So it's a pretty nifty tool. Okay, so I need to flatten the display to do that, and then move my entire rig closer because I can't see it. This is part of the nice thing of getting old is your eyesight can your eyesight doesn't deteriorate that fast, but the ability to focus goes first. So even though you still have 20/20 vision, your glasses doesn't work universally anymore. So I have to use my bifocal area when I'm looking at this close. Okay. So originally we have, so let's say this is the array. Okay, it has 5 structures in it. Is that okay? And each structure has 2 members. The first member is the value. The second member is the next. Okay, so this is basically element 0. This is element 1. This is element 2. Element 3. And this is the last one. This is our element 4. Because the array has 5 elements, so the last one has an index of 4. So are we doing okay so far in terms of how it looks like in memory? So in this case, the lowest address is right here, and then the highest address is right here. Does that make sense? Okay, so memory just increases as we allocate more items on the stack. So what we want is to create a linked list out of this, which means I want this next member to point to the address of the next structure. I want this next pointer to point to the address of the next structure, and so on. Okay. The last one, the symbol to represent it is, sometimes we use the ground symbol, sometimes we use something else, but the bottom line is this n here needs a special value to indicate, oh, this is not a good pointer value. This is a null pointer, null, which also exists in C and C++. What is null, by the way, null? What does it translate to? 0, exactly. So 0 is really special in C and C++ because 0 automatically casts to pointers as well. If you have a pointer type and you assign 0 to it without casting it to a pointer, it actually works. So 0 is a very special constant in C and C++. Okay, so now the question is, how do we get this done in terms of C code? Because once we know the C code, then we can think about how to translate that into assembly. So there are several ways to do it. You can basically just have a pointer, initial pointer to point here, and say this pointer, the pointer n, or the member n here, the p next, is going to be the address of the next thing. Where's the next thing? Well, since this is an array, if I add the size of a structure to the pointer to the address of the first structure, that should become the address of the second structure, right? So that would be the quickest and easiest way to do it. And then we count how many times we have done it, okay? So we'll do it 1, 2, 3, 4, which is 5 minus 1, the number of nodes minus 1. and then when we get to the last one, we just say, okay, this is the last one. It has no next, so we'll just put a 0 into that place. Is that okay? All right. So I'm going to switch back to the notepad here, and then we'll write some code. All right, so the initialization of this is we need a counter to keep track of how many times we have done something. So we'll use uint underscore t. We'll just call it n, which is a counter. And n is initialized to 4 because we have to do it 4 times. And then we'll need a pointer. Instead of using array indexing, we are going to use a pointer. So we have node, struct node. I'll just call this PTR as a pointer. And then pointer is initialized to the beginning of the entire array. And you can do that in C and C++. Because in C and C++, an array is really kind of the same thing as a pointer. I forgot about the asterisk. Excuse me. There we go. So now they should work. And now you just need a loop to go through something 4 times. So that loop is rather simple because you just have to say while n. You can also use a for loop, but I'm going to use a while here. The last thing you do is to decrement n. N is not useful for anything other than just counting. Okay, that's just a counter. And then each time you get in here, you basically say whatever PTR points to, I want its next pNext member to point to the next structure compared to what pointer is pointing to. Is that okay? So we are basically, is this notation familiar to you? Is that okay? Because sometimes, I have students from cisp310 who have never seen this notation. So are we good with this one? Yep, okay. So we will say that this is basically PTR plus 1. Okay, now we have to take a little pause here. What exactly is PTR? PTR is a pointer to a struct node. So PTR or pointer plus 1 is not really just adding 1 to the address of a struct node. It is actually moving on to the next struct node. So when you have pointer arithmetics done on, when you have pointer arithmetics, the number that you're adding or subtracting is not indicating the number of bytes as an offset. It is indicating the number of things that the pointer is pointing to as units. Because pointer is pointing to a struct node, this 1 is basically specifying the size of one struct node. So we are moving on. This expression here, pointer plus 1, is specifying the address of the next struct node in the array. Is that okay? All right, cool. And that's kind of the only thing we need to do, more or less. We just have to remember to increment the pointer so that now we are just moving on to the next one. Okay. There is a way to make this code a little bit shorter. Okay. Well, there are 2 ways to make it shorter. First of all, we can put the decrement here in n minus minus. Okay. The second thing is we can use the plus plus, and then instead of pointer plus 1 here, and then we have plus plus pointer below, we just have plus plus pointer. Okay. So if you want to use the least number of lines of code, because you're in a competition and that's what you're supposed to do, you can do it that way. Does anyone want me to change the code to use the least number of lines of code, or leave it the way it is, which is more clear? Okay, how about this? I'm going to copy and paste it. So we'll keep this version, but I will give you the alternative version. So this way we are not destroying the only one that we have. Okay, so first of all, we can change this to n minus minus. The reason why it is n minus minus and not minus minus n is because the decrement is occurring after we check whether n is 0 or not. If you do a minus minus n, then you are actually subtracting before you compare which is going to only go through 3 times instead of 4 times. Okay? But since I have the n minus minus here, I don't need the minus minus n here at the end anymore. So I can get rid of that. So the second thing we can do is to look at pointer plus 1, and then the next line is really pointer equals pointer plus 1. So it's kind of, you feel there's a redundancy, because plus plus p pointer is really the same thing as saying pointer equals pointer plus 1, right? So now we can definitely see there's a redundancy. Okay, we already calculated what is pointer plus 1, and then we store that into p next. Why can't we just store it into pointer itself as well? So there are 2 ways to simplify this operation. So one thing you can do is to do it like this. But this is not recommended. The reason why this is not recommended is you don't know how the compiler is going to look at this. Okay, at least I'm not aware of any C specification that guarantees an evaluation of left to right. The problem is you might change pointer first before you try to access a member of pointer or what it points to. Then it has a problem. Okay? But if you change it to a pointer plus plus pointer, I think that will work in most cases, but it's still not guaranteed. Yep.
Isn't that still going to increment pointer before it assigns?
It depends on the evaluation. So if a compiler decides to always evaluate the right-hand side and then evaluate the left-hand side to figure out where it's going to store that value, then this is not going to work. On the other hand, if the compiler says I'm going to parse from left to right strictly, I will figure out the address of where I'm supposed to store the right-hand side, and then I evaluate the right-hand side, then this will work. So it is still tricky because it still depends on the implementation of the compiler. Yep.
What if we put the parentheses? Isn't he going to guarantee that? Like in front of the plus plus pointer at the end.
In front of the plus plus?
Yeah.
Like that? That won't change it won't change the fact that the compiler still can decide when to compute the address of where you're supposed to store that thing, and when to actually increment the pointer, because the compiler probably can choose which way to go. I'm not aware of any C++ specification that dictates when that increment is to occur. So we have a problem. So the only way to do it without a confusion is to do it the way that we did it already. Yep. So we're going to erase this one, and just basically say that there are cases where yes, we can potentially make the program shorter, but then we get into a territory where your program may work like for many years, and then the compiler updates, and then suddenly it doesn't work anymore. And those problems are very difficult to spot. It's not the same thing as you go in, you change your code, and then it doesn't work, because then you can still use a revision control, figure out what you did to the program. Okay, this one is like, but it used to work, now it doesn't work anymore. We just updated the compiler. One of the worst kind of problems to diagnose. Okay. So this will initialize the first 4 structures, and there's one last one that we need to deal with. The last one is going to be whatever pointer is pointing to, and then the p next of that thing is just going to get a null. So instead of using null, N-U-L-L, all uppercase, I'm just going to use a 0 here because that's basically what it is. So are we good so far with the C code? How to initialize an array of structures so that it becomes a linked list. We good so far? Okay. So now the next question, which is why we have this class, is how do we do this in assembly? Now, if you have any questions, please go ahead and ask those questions, because if we wait to answer those questions, that can be it would just kind of stack up. Okay, so stuff would just kind of stack up. So the first thing we need to do is to represent a structure or node in this case in assembly. There's no structure definition in assembly language programming. It is not only limited to TTP-ASM. You can look at the Intel assembler for the x86 architecture, which had existed for eternity. Okay, it doesn't have any structure. Okay, it doesn't understand what a structure is. You can look at the GNU assembler. It doesn't know what a structure is either. Okay, so at the assembly language programming level, there's no these concepts do not exist anymore. It's just like a while loop doesn't exist in assembly language programming. The concept itself is not encapsulated by any syntax at all. So what we do in assembly language programming then is, one thing we can do is to use label definitions. So my tradition, this is just a convention that I use, is to use the name of the structure followed by the name of the member, and then define that to be the offset in number of bytes from the beginning of the entire structure to that particular member. Is that okay? So does it make sense that since value is the first member of the entire structure, the address of the member value of a structure is really the same thing as the structure itself? Right? Because it's the first thing. It's kind of like the first element of an array really has the address of the entire array because it's the first one. Okay? So I use 0 to represent it. And then the next one, which is p next, is going to be node value 1 plus. It is 1 byte after that. Okay? Does that make sense? Okay? So I have this particular convention of using the name of the structure, which is node in this case, and then an underscore, and then the name of the member. So this way, it is unlikely that I will have collision. It's unlikely that I will have the same label used in two different contexts. There's one more thing I need to define in this case, and it has to do with the size of the entire structure. So I just call it size here. And that's just going to be the last member. In this case, it is p next, plus the size of the last member, which is also just 1 byte. So now, if you look at the definitions, node underscore value is nothing more than just 0 by itself. Okay, that's pretty clear on line 1. But node underscore p next is also really simple. It really is just 1, okay, because it's 0 plus 1. And then when you look at node size, it's just 2, because it's 1 plus 1, which is 2. But the reason why I define all of these using symbolic names is so that in the future, if I want to have another value defined inside the node, I just have to change the definition, but the references to the symbolic name do not need to change anymore. Okay? So there's a value, there's a reason why we want to use symbols or labels in this case to represent the offset of a particular member from the beginning of the structure. Are we good so far? All right, cool. All right, so now we get into the implementation of main. Oh, by the way, there's also num nodes. Okay, num nodes can be treated as a label as well because it's just 5. Okay. All right, so now we have main, and before we get into main, we have to initialize the stack pointer. And then this is the official entry point of main. So in main, the first thing we need to do is to allocate an array of 5 struct nodes. How do we do that? So that means we have to decrease the stack pointer by the number of bytes that the array nodes is going to take up. Now this is all based on my toy architecture. So we kind of know, using these numbers, we know how many nodes there are. We also know how big each node is. So what do we do to allocate for the array itself? Yes, so we decrease d 10 times But if I want to utilize the symbol instead of decrement D, like repeat that statement 10 times, or I can try to do something like this, right? Okay, so I'm going to do it the wrong way first, and then we'll fix it. Okay, subtract from D that much. That would do it, right? So this is going to be allocating nodes from the stack as a local variable, right? So why did I say this is not really the best way to do it? It's not the best way to do it because 10 as a constant doesn't really make use of the labels that I have defined. If I want to change the array to have 10 elements, I have to remember to change to this because otherwise, it will only be initializing the first 5 out of 10 nodes. It's not going to initialize the entire array. Okay, so that means instead of sticking a 10 here, I should use some calculations. So that's just going to be num nodes, right? Node underscore size times. Because it's the size of each structure times the number of structures in the array. That becomes the total number of bytes that I need for the entire array. Is that okay? So now in the future, if I decide to change the number of nodes in the array from 5 to 50, I don't need to do anything except for changing the label definition itself. If I want to make the structure bigger, so instead of having just a single value, it has a flag and then something else, I do have to mess around with line 1, 2, okay, a little bit to insert a new label definition for whatever I want to define. But once the size is calculated correctly, I don't have to deal with I don't have to do any further calculations myself, because I'm referring to the symbolic names. So as long as the symbolic names are defined correctly, I'm good. Is that okay? So most assemblers support this kind of operation, probably not in a postfix notation, but it can support like calculations when it comes to constant calculations or compile time constant. Okay. All right. So this will allocate for nodes, and then I need to allocate for n. So decrement D. So we have allocation for local variable n, and then we have decrement D again, which is allocating for pointer. Is that okay? So at this point, which is really at the entry point of the code itself, the stack is going to look exactly like this. The stack pointer points to the local variable pointer. 1 byte on top of that is n, the local variable n, and then 1 byte on top of that would be the array nodes. Is that okay? So instead of having to memorize that in my head, I'm going to define some additional labels so that I can use label names for that purpose. So I'm going to say pointer is 0, which is basically saying that pointer as a local variable is pointed to by the stack pointer itself. There's no offset from where the stack pointer points to and pointer as a local variable. Next one up is n, which is ptr 1 plus. Okay, 1 byte on top of pointer is n. And then on top of that is nodes, which is 1 byte on top of n. So now I know, using a symbolic name, nodes, I now can say, oh, okay, it is 2 bytes. Nodes is 2 bytes from where the stack pointer points to. So the nice thing is it is in symbolic name. So this way, if I change anything in the future, it's easy to adjust. Okay, the program doesn't have to be changed extensively if I need to make any changes. All right, with all of this stuff done, I'm going to implement the program. Yes? Okay, so that's a good question. This is also why it is nice to allocate the stack in a backwards manner. Okay, I'll show you a picture. Let me go back to Zerno first. There we go. All right, so let me draw the stack first. Okay, so okay, it has palm rejection, but only works when the pen is detected first before my palm touches the screen. So now it works. So we'll draw the memory like this. This is high memory address, this is low memory address. Okay, so let's say this is where the allocation starts. We allocate 10 bytes here. This is for nodes. So it has 1, 2, 3, 4, 5 individual members. But nodes as a symbolic name is really referring to this location because it is 10, it's the stack pointer minus 10. So that makes nodes as a symbolic name refer to the offset from where the stack pointer points to the very beginning of the entire array. So that's why it is nice to allocate in that particular fashion, because it is automatically the beginning of the structure. But to complete the picture, okay, this is the next thing, which is was it N or PTR? I cannot remember. The next one that we declare was N and then PTR. Okay. So this is N, and now we have PTR. The stack pointer, after all this allocation, is pointing to the pointer, and that's why the displacement is 0. The next one up, which is 1 byte away from where the stack pointer points to, is local variable N. But when you look at the first byte of nodes, it's only 2 bytes away from where the stack pointer points to. So the symbolic name actually does work out, really nice. Sure. Yep.
Just kind of quick thing. So above n we have nodes 0, and then nodes 1, like the first element of the array.
So in terms of node 0, this is node 0.
Yeah.
This is node 1, 2, 3, and 4. Yep. So in terms of elements in an array, they just increment. They just go for the next location, the next location, the next location. So is that picture helping? All right. And by the way, this is also not specific to TTPSM or the way I teach the class. Okay, if you look at any C program, C++ program, it's arranged basically exactly the same way. When you look at classes in object-oriented programming, it's not exactly the same because it also contains pointers to functions and stuff like that. So there are hidden stuff that you don't see. But for the most part, okay, when you look at an object in C++, in object-oriented programming, it still follows kind of the same scheme where each member is taking up a place within a block of memory structure. Except you do have hidden stuff that you do not see because when you have methods. So okay, this is a little bit of a digression. When you have normal member functions, all the normal member functions belong to the entire class, so the structure only needs a single pointer to point to a reference table of the class itself. But when you have, I'm trying to remember the correct name, virtual functions, that's it. So when you have virtual functions, it's a little bit different because virtual functions are not affected by casting to a superclass, so that gets attached to the object itself. So little things that are slightly different, but we are not going to get into object-oriented programming in this class. But in terms of that picture, are we good? Okay, all right. So now we switch back to the code. We want the C code, and then we want the assembly code. There we go. So the first thing is we need to initialize 4 and N to 4. So there are several ways to do it. And this time I don't really need to use my pen. Just have to remember to take it with me. So we have we LDI A with 4 first, which is the right-hand side. Then we have to compute the address where we are supposed to store that. So the typical sequence is LDI C with the name of the variable that we want to access. In this case, it is N. And then we say add CD. So now C is the address of N. And then a single ST instruction will now store the value of 4 into C. well, into n, sorry. So n equals 4 is done here. The next one is to initialize pointer itself. Well, that one is a little bit more involved because the right-hand side is not just nodes, okay? In other words, this is not the right-hand side because it is only the displacement from where the stack pointer points to nodes. It is not the actual address of node. It's kind of like, where's your house? Oh, my house is, 3, houses down from Tax house. Okay, it's that 3. But if somebody wants to ask you, what is your address? 3 is not your address. Okay, you actually have to compute the street address based on the fact that you are 3 houses down from Tax house. So now you have to know where Tax house is, which is what the stack pointer is pointing to. So that's why you have to add the stack pointer to A, then it becomes the address of nodes. So now register A is the address of nodes. And then we'll do the same trick with the other side. We load PTR into C, or pointer, and then we add D to C. So now C is the address of pointer. And we want to store the address of nodes into pointer, not the address of pointer, but pointer itself. So once again, we have a store instruction, and we specify A, which is the address of nodes, like that. So this is implementing pointer equals to nodes. Are we doing okay so far? All right. So that finishes lines 15 and 16 of the C code. So now we are moving into the while loop. Okay, so we are implementing a while loop. So the typical thing that I would do, especially when I can use an editor, is to specify all of the constructs within the loop first. So we have a while begin label, a while end label, and then we have an unconditional branch back to the while begin at the very end of the body of the loop. So we know we need at least this much. Then we go back in here and specify the condition. The condition is while n, blah, blah, blah. So when we say while n, it is just implicitly comparing n to 0. Okay, it's asking, is n different from 0? If n is different from 0, it is true. So it's basically comparing to 0. But we don't really need to compare to 0. We don't need to put a 0 into a register and then do a CMP, because the AND instruction can do that. Was it the AND or the OR? It was the AND, right? So we can AND, we can put the value of n into a register, and then we can AND that register with itself. That will set the Z flag, which is what we need to decide whether to go or not. Okay. So we just do the same trick here. We have a lot of LDI, C, this time with n, and then we add D to C, and then we dereference it. So in this case, it's a LD instruction. Register C is fine. We'll just dereference C back to C. So at this point, C is n, and then we just AND C with C, and then we only have a JZI instruction. So we have to say, okay, if it does equal to 0, do we continue with the body of the loop, or are we exiting out of the loop? We're exiting. Okay, so we go to while end, which also means at this point right here is the body of loop. Is that okay? So remember, in the exam, in the final exam, when you are asked to write code, you can kind of do it like this by using the insert symbol. So as long as it is clear to me, this block of code goes in here, this block of code goes in here, this block of code is going into here between those two other blocks, it's fine. Okay, I'm okay, totally okay with annotations like that. So that way you don't have to kind of write some code and then leave. You don't know how much space you have to leave, for the code that you're inserting. All right, so in the body, we got these 3 lines that we have to use. So on the first line, which is line 19 of the C code, we have to compute what is PTR plus 1. So we have to get to pointer first. So LDI C PTR pointer, and then we add D to C. So at this point, C is the address of pointer, but that's not what I want. I want the actual pointer itself. So I'm going to dereference, okay, so LDCC. So now C is actually the pointer itself, but that's also not what I want. I want to get to the next one, right? I want to get to the address of the next thing. So now it's time to implement this +1. But remember, this is pointer arithmetics. It depends on the type of what pointer points to. So you're not adding 1, you're adding the size of whatever the pointer is pointing to. In this particular case, pointer is pointing to a node, and the node size is just node size. There's a symbolic name for it. So that's pretty handy. So we have to do LDI A, use a different register, node underscore size, and then we perform the addition, add CA. So now C is actually pointer +1, typed. Are we good? So that's our right-hand side. Now we need to look at the left-hand side. The left-hand side this time is, looks kind of icky, right? I mean, it looks like, oh, how do we do this? Well, you just have to think about the order of things, okay? You can't really worry about pnext until you get to pointer. Let's get that done first, okay? So at this point, register C is used. I don't want to mess it up. I can still use register A and B. So I do LDI again, register B with pointer, add BD. And if you think that you may not be able to keep track of which register has what, I strongly suggest that you comment, okay? Because if I don't comment, I cannot remember either. So now this is that. But it's not pointer that I want, because I want a member of the structure pointed to by pointer, okay? So I definitely need to dereference at least once. So I need to LD B with B. So now B is actually just the pointer itself. So now the question is, then what do? We get pointer now, but it is not the entire structure. It's not the first byte of the structure that I want. We want the member pnext. Oh, wait. We already use a symbolic name to keep track of the displacement or the offset of a member pnext from the beginning of a structure. If I know the beginning of a structure, I know how to get to each member. Can anyone remember the name of that symbol? Node underscore pnext. Oh, okay. So now I can LDIA with node underscore pnext, and then just add it to register B. So now P is the address of PTR points to next, pnext. This is the part where it gets kind of icky, right? Because which means a picture can be helpful. So let me switch to here. Let's see, scrolling works. Yep, okay. Okay, so what we have here, actually I can still use this picture. It's just a question of, how do I want to denote that? Because there are 3 things here. Okay, the first one is PTR. Okay, so how do we get to this byte here, which is the pointer itself? Well, we just say whatever the stack pointer is, add pointer as a symbol to that thing. That symbol is just 0, right? So we get to the address of pointer. Then we dereference, so we can actually get to the byte at that location. That is the actual pointer. So in this case, the pointer itself is actually pointing to one of the elements. I don't know which one, because it depends on which iteration we are talking about, but it points to one of the elements. But when I say it points to one of the elements, it's pointing to the beginning of the entire element. Is that okay? So a pointer is pointing to the beginning of a struct node. I don't really need that struct node itself. I need the address of a particular member because I'm overwriting member P next. So what you need to do now is to say, I need to adjust this pointer here just a little bit. Uh-oh, wrong tool. I just click on the eraser tool. Nope, I didn't click on the eraser tool. Maybe I accidentally clicked one of the buttons. Okay. So this little displacement here, that's what is what node underscore P next is defining. It's that little distance. If you can get me to the first byte of a structure, node underscore P next can get you to the address of the member P next. Is that okay? So switching back to our code, we're pretty close to done now. So now what we can do is to say, oh, okay, so since we have the address of the member that is going to be changed, and we have the right-hand side is stored in register A, register C. So register C has the right-hand side. Register B has the L, or the left value, or the address of the value that of the place you want to change. So now we just need a ST instruction, ST B, which is the address of the byte that should be changed, and then C is the right-hand side. So that finishes line 19. Is that okay? So everything from here, from line 35 to line 46 in assembly, is implementing line 19 in C. All right. The next two lines are relatively simple by comparison. Okay. So on line 20, we just want to increment pointer. Okay. So LDI C with pointer, add to CD. So C is now the address of pointer. We want to keep this one around because we want to store and change that location. So we want to dereference into another register. Register A is still available, so it's register B. I'll use register A. So A is actually pointer at this point. We increment it, increment A. So now A, register A, is pointer plus 1. And then we want to store it back. And that's why I didn't mess up register C, because now I can use the same register and then just put it back. So this accomplishes PP PTR. I mean plus plus PTR. Is that okay? And then the next one, kind of the same thing, except it's a decrement. So it really is about the same thing. Load I C with N this time, add to CD. So that will make C the address of N. Keep it around. So I load the value of N into register A. And then we decrement. Okay, so we do a decrement on A. So the A is N minus 1. And then we just have to store it back to whatever C is pointing to. And that accomplishes minus minus N, or decrement of N. Are we good so far? And then we have one more thing to do when the while loop ends. When the while loop ends, we have to store a 0 to the member P next of PTR. Well, we kind of know how to do that already. LDI A with 0, that's the right-hand side, easy peasy this time. And then we have to compute the address of the left-hand side. Kind of the same thing, LDI C with PTR, add CD. So that C is now the address of PTR, or pointer. Do a dereference, LD C with C. So now C is actually the pointer. which is the address. Okay, so C at this point is the address of the structure where the member P next is going to be changed. Okay, but it's at the beginning. I just need a little bit and nudge it a little bit so that we can get to P next. So we use LDI B, register A is used, we use register B in this case, with node underscore P next, which is the offset from the beginning of a structure to the member P next. And then we just add that to whatever C has. So now C is the address of the P next member of the structure the pointer points to. Don't ask me to say that sentence one more time. Is that okay? All right, well, isn't there where we want to put the 0? Yep, okay, well, then we just do a store. So now this accomplishes the P next member of whatever the pointer, whatever structure pointer is pointing to, is now getting that 0. And that's the end of the code. So now we have to deallocate. So for deallocation purposes, you can, let's see, what is the quickest way to deallocate? Okay, you can do it this way. You can do LDIC, okay? So the way you do it is you figure out how many bytes you have used up. And how do we know that? You look at the highest, okay, let me switch back to the picture. And scroll up like that. Yeah, so look at this picture here. So you want register D to go back to before. So now you need to basically add up the number of bytes that all the local variables have used up. Local variable pointer, local variable and local variable nodes. So for the most part, you just need to add the size of the last local variable, which is nodes, with the size of it. Add nodes to the size of that local variable. That becomes the total number of bytes that we have used up for all the local variables. Is that making any sense? Okay. So that means the deallocation can be done. The allocation can be done the same way too, but I kind of did it in a slightly different way. So you basically just say it is nodes, which is the number of bytes from where the stack pointer points to the local variable nodes. But then you also look at the size of that thing, which is node size times the number of nodes. And then you add nodes to it. Okay, I'll do it in a slightly better way. So we first calculate how many bytes do we have in the array. And then we say, let's add nodes, which is the number of bytes from where the stack pointer points to that thing. So this becomes the total number of bytes we have used up for all the local variables. And then in one single add instruction. So this time we want D to be on the left-hand side because we are really changing D. We are moving D from, let me switch back to the other picture. Okay, it's actually right behind this. There we go. Okay, so this time we are adding D to nodes plus node underscore size times num nodes. So that would make D all the way back here, which is in this case 0 because main is, we are not in an actual subroutine, but we should have deallocated every single byte. Is that okay so far? Yep.
Which way is better? The one that we do individually or like this? Because from that programs we were doing it decrementally.
Correct. So the other way when you're allocating the individual decrements, let me go back to that code first, right here. So this one, you kind of have to know the size of every single variable in this case. So this one, if you do it this way, it takes a little bit longer, but it also makes sure that we understand what we are decrementing.
No, I mean the increment when we deallocate.
When we deallocate?
Yeah. Before we were doing decremental.
Increment. When we deallocate, we increment.
I need to. I think you said it's faster that way.
Oh, this way is definitely faster, way faster. Because instead of using a whole bunch of increments, you just have 2 instructions. Yep.
I'm not entirely sure how that math worked out. How did it grab the pointer and head as well?
How it grabs.
Yeah, how did it deallocate
Oh,
the
okay.
pointer as well? Because
So-
it looks like it's getting rid of nodes.
So no, it get rid of everything because pointer is 0, n is 1, nodes is 2,
Okay.
right? And then node size is 2, num nodes is 5, so that's multiply those 2, you get 10, right? So now you have 2 plus 10, which is 12. And 12 does match the number of bytes that we have used up for all the local variables. So it does work out, but it has to do with the ordering of which variable did we allocate first. And nodes was the first one to be allocated. Yep.
If we're just deallocating everything,
Yep.
would it be possible to do
Okay, so the question is, since we're deallocating everything, can we use subdd? In the case of main, yes. But main is a very special case because it wasn't called by anyone else. But if you're doing this in a different subroutine, then you have to restore the stack pointer to point to the return address, which is right above all the local variables. Then you can't use that approach anymore. So you still have to calculate the total number of bytes allocated to your local variables. So yes, in this specific case, by the time we get here, by the time we get the halt instruction, D should be 0. But that's only because this is the entry point of the entire program. Is that okay? I know we are running a little bit over time, but I came late a little bit today too. So do you guys want to see this run and kind of see how the memory is initialized and stuff like that? Yeah? Okay. And potentially maybe see embarrassment because the program doesn't work. I would live for that. Hmm? Well, I mean, it's probably some minor mistake that I make somewhere. All right, so I'm gonna have to flip the screen back up because I can't see a single thing. Okay, so we also need the assembler. So switch back to here. Yeah.
All that like wasn't even doing anything with them. It was just setting them up, making sure they're all pointing to the next one.
Yep. But the concept of how to access a particular member of a structure, that's really kind of what I want to show is what if it is on the right hand side? What if it is on the left hand side?
In that case, how come we didn't, when we were putting the values in, we didn't use like an expression to make sure it's 1 less than the number of nodes?
We use a single decrement because we know it is only 1 byte long thing.
No, I mean, because we have n is 1 byte, but we didn't like put 4 into it for a while.
Yeah.
Why didn't we like do like number of nodes minus 1 that way?
Good point. I will fix that. Because I forgot. So that 4 is here. Okay, very good. Good catch. You got me. So it's going to be num nodes 1 minus. Are you guys starting to get used to the postfix notation, or are you guys still going like, ay? It gets some getting used to, but once you get used to it, it's actually pretty, it's useful. Okay, I'm just looking for the end of the program because there might be some, oh, okay, there's no leftover from the previous program. Good. All right, so file, download as. We'll call this linked list. Oh, L-link. Okay, fine. We just have to use it consistently.
Type this into I can't take note of it. I need notes.
Well, imagine those days when people do not even have assemblers, so they have to kind of like look up the opcode and tweak the ones in binary and then figure out how many bytes are between this thing and that label. All right, so I have relative faith in myself, so I'm going to do a Control K and just run it. It's done. Okay. So the only way you can tell whether there are several ways you can tell whether the program is working or not. The first thing is to look into the register bank and make sure register D is balanced. Okay, that looks good. Okay. And then the second thing is to look at the content in RAM and see whether we have the array initialized. So that doesn't seem right to me. All right, so what we'll do is we'll figure out what is the increment of to the next one didn't work, because these things really should not be sequential right next to each other. But we can try to figure out how memory is used. The last 10 bytes were used for the entire array. So we are talking about 4, 8. So we are talking about this portion here. That is being used for the entire array. This is our n, which is good. N got to 0. That's good. And this is our pointer. So pointer gets to FA, and FF, FE, FD, FC, FB, FA. That's the last location that got changed. So instead of incrementing every other, it is only incrementing by 1. So I wasn't adding the size of each node correctly to the pointer as I advance to the next location. So getting back to the code, I can point out exactly where the mistake is. So I will refer to the C code first. So in terms of the C code, this part was not done correctly, and that's why it's only moving to the next byte. So now we get back to the assembler code and figure out which part are we talking about. It's in the loop. It's the first thing. It is the calculation of this. So it's this part that didn't that wasn't implemented correctly. So node. Node size should be 2, and it depends on how I did it. Did I did it correctly? So node size should be 2, according to the equations. But then we have to look at the implementation of the assembler, because if I make a mistake in the implementation of the assembler, then we have a problem. So now we look into this and go like, okay, what is the value of node size? So node value is 0. Node P next is 1. Node size is 2. So node size is actually has a value of 2. So that part is correct. And I can even go to the assemble tab and see how the code is compiled or assembled and tell whether it is working correctly or not. So we are looking at this line here. See this 02? That is correct. That 02 says we are actually loading 2 into A, and then we are adding A to register C. So that part was actually correct. But yet it is only incrementing by 1, affecting only the next byte. Well, move down a little bit. We're adding A to C. That's the right-hand side. Now we want to look at the left-hand side and see whether we actually store that correctly. So we got the address of pointer. This is pointer itself. This is oh, that's exactly the mistake that I mentioned earlier. Nope, nope. This is not the problem. The problem has to do with, okay, let me check the memory first. Are they skipping by 2? Nope, they're not skipping by 2. Is this one supposed to be F8? F8 is all the way here. This is F8. So this one is initialized correctly. So the +2 part is not the problem. It's incrementing the pointer that is the problem. Where's my... There, okay. It is this one that was implemented incorrectly. Look at this. Increment pointer, we'll just add 1 to it. Right here. We shouldn't be just adding 1 to it, right? Yeah, that was the bug. All right, well, LDI b node underscore size, add a b, and then get rid of this increment. There we go. Okay, double check. So we got pointer, we add node size to it, and then store it back. Okay. All right, so Control A, Control C. Go back to the assembler. Oops. And then go up. Control V again. So I load. Oh yeah, the Control Alt, actually changed the cursor position. There you go. Yep. All right, so let's go ahead and re-download and okay, let's close that first. Go back to the emulator. Control R, reset everything, and then reload the image. And then Control K, run it, and then re-examine the memory content. Oh, now it looks a lot better. Okay, let's double check. This is location F7. This is location F6. So F8 is here. It is in fact the beginning of the next structure. This is F8. This is F9. FA is the beginning of the next structure. This is FC. This is location FC. This is location FB. Pointing there, that is correct. This is pointing here. This is the last one, which has a null pointer. So now it gets everything initialized correctly. You can also see that the pointer is also at the right correct place because the pointer is FE, which is the right place. FE is the address of the last member of the structure, which is where it's supposed to be. So that's kind of how you debug a program. Even though we don't have a debugger, and for the most part, a debugger doesn't help that much when you're writing in assembly code. In C code, it helps a lot. Okay, But in assembly code, you can stop at a certain point and check on things, but you basically have to look at the leftover, okay, whatever whatever trace the program has left over, and try to analyze it and ask, why is this happening? Why do we have consecutive bytes updated? Well, there are only two places where the +1 versus plus the size of each structure is important. I checked the wrong part first, and then because it's actually the increment of the pointer itself that was responsible for that. But there were only a few places where it can account for that kind of behavior. And that's, if I could teach debugging techniques and skills like that, I would definitely want to teach that. Unfortunately, it's not just knowledge. It has a lot to do with, some of it is personal too. Like I have my favorite bugs to make, okay, and you probably have your own. So where you look first is kind of personal because some people like myself, a lot of times I forget the post increment in the loop or post decrement in the loop, so it becomes an infinite loop. So that's actually where I would look first when something doesn't work and it's an infinite loop, okay? But eventually it boils down to you have to kind of know what type of favorite mistake you tend to make, look in those first, and then if it's not one of those, then you have to kind of analyze the result of the program to try to figure out what can cause that to happen. So instead of saying oh, my program is not working, the real question to ask is, how is it not working? How is this different from what I'm expecting? And then from that difference, you can try to think of, okay, what code can potentially cause this to happen? What code has access to these locations? That will help you limit to what portion of a program is incorrect, and then how it is also incorrect. A good, effective programmer is not one who doesn't make mistakes. It's one who can find the mistakes quickly and fix it correctly. So that is, I remember, I know we're past the end of the class, but there's one Dilbert cartoon. I got to show you that one because it's really good. Dilbert, Wally, write me a minivan. Okay, well, apparently a lot of people like that. So where's the picture? Okay. Well, I can always do an image search. Yeah, there we go.
You want the one above it, the one to the left. That one.
Okay. Our goal is to write bug-free software. I will pay you a $10 bonus for every bug you find and fix. And then Wally said, I'm going to write me a new minivan this afternoon. So not only is he not fixing his bugs faster, he's trying to intentionally make more bugs. And there's also a ratio. IBM did a lot of study, like a long-term study, of the number of bugs introduced per bug fixed. So it should be hopefully a relatively low number, like 0.2, but it turned out to be a pretty high number. You can look that up too. But that basically is what as a software engineer, as a coder, programmer, that's what differentiates a good one from a ineffective one. Not a bad one, just not effective. All right, well, that's the end of today's lecture. I think I made up for the lost time, more or less. I'm going to stop the streamer. Well, there's no new lab assigned, so there's just the one that is supposed to due today, and there's also the one that that's due on Wednesday. So swap is due today at the end of the day, and then Fibonacci is due on Wednesday at the end of Wednesday.